All right, thanks for joining us for this third installment of the NMR video series. The I think in the last video we talked about what the chemical shift and the integrations area under each peak help us interpret in terms of clues about the structure of the molecule we are analyzing. The last, but one of the most important, is the splitting pattern that you might or might not see for each signal or each peak. So that's the main focus today. So if you look at the NMR spectrum of this molecule, where there's these three hydrogens, and hopefully it's apparent to you by now that these two hydrogens would be equivalent because of the rotation that's possible around the single bond, which makes these two equivalent, right? So all of that to say, you should see two signals. One signal is going to be worth two hydrogens, so you would have twice more area under that peak than the signal corresponding with this proton. Okay, so those are these two signals. Now, if you zoom in close, you'll find out that they're going to be split in different ways by both of these signals. Now, the very common confusion that I see is the students think that like this splitting pattern has to do with what that specific signal contains in terms of how many protons. Now, this HB signal corresponding with that in the structure is split into three peaklets. That doesn't mean that this peak has enough protons or it corresponds with three protons. That's not what this means. This proton is or signal is split into three peaklets because of the surrounding influences. So you have to look at the surrounding protons. And what this tells us is how many neighboring protons that HB has that are impacting it. And that's the n+1 rule. Okay, if you have two neighbors, you'll have three peaks or peaklets, or the peak will be split into three. If you have one neighbor, it'll be split into two. That's n+1 rule, and that's because those neighboring protons have they could be either up or down spin state, and that we're going to get into that in a sec. Okay, so now this HB proton, as you can see in the structure, because in this case we happen to know what the molecular structure is. There's two protons on the neighboring carbons, and that's why it's split into three. Now this HA, it's a doublet. That's not because there's two hydrogens for HA. It's because HA has one neighbor, right? That one neighbor splits it once into a doublet. That's what that tells us. And
right, let's take a look at that sort of the more detailed reason why these split the way they do. This is basically the same molecule as the one on the previous slide, except chlorines are replaced with bromine atoms. Here we're taking a look at the signal corresponding with these two protons, which are equivalent, which are split by their single neighbor, which is that proton, into a doublet. And why is that? Well, this neighboring proton, remember we're looking at the signal for these two, its neighboring proton could be sometimes in the alpha spin state, which is the same direction as the external magnetic field. Here's the external magnetic field. Or it could be in the beta spin state, which is the sort of the opposite direction of the external magnetic field, and so for that reason it's a slightly higher energy state. And these guys, right, being magnetic beings, they could feel the influence of that neighboring proton, even though it's a really tiny magnet, right, this tiny proton. But that's enough to split the peak into two, because about half of them are in the alpha spin state. The other half is about approximately half is in the beta spin state, and so that splits it into about 1-to-1 ratio, which is a doublet. Okay, so yeah, well, I haven't been pressing the button here, but HB can feel the alignment influence of that adjacent proton HA. That's what we just said, and it could be the neighboring HA proton could be either de-shielding or shielding, right? So this is the shielding effect when it's opposing it, and so that's why it's a doublet. Now, let's take a look at the splitting pattern for HA. So now we're looking at the signal that comes from this proton. They have two neighbors. Now, because they have two neighbors, statistically, there's a quarter of a chance when both of them are in the alpha spin state, and then there's a quarter of the time they both just happen to be by chance coincidence happen to be beta spin states. Now, technically, there's a little bit of difference in those populations, but like statistically speaking, you could think of them as just a flip a coin chance of whether they would be in the alpha or beta spin state. Okay, and about 50% of the time, because there's two scenarios, one could be up, one could be down, or one could be beta, I should say, and then the other could be alpha. And so there's twice more likelihood that there's that like sort of alpha and beta opposite combination situation. So that's the middle. If they're both de-shielding, then your peak would be shifted downfield. If they're both shielding, they would be shifted more upfield. And so for that reason, that when there's two neighboring protons affecting your signal, that signal will be split into a triplet. I hope that explanation makes sense. Likewise, if you have, if we look at this signal for this HA, which has three neighbors, right? These could be all up or all down, or one up, two down, or two up and one down. And those are the possibilities that are playing out. And this is just the statistical possibilities. There's right, like fairly low chance that there's all up and then all down, but there's a pretty good chance that they're just one up, two down, or two up, one down, right? And so that's why this statistical distribution, and it's going to be a quartet or split into four peaks, and in reality the peak would look like this. Okay, and because there's a statistical distribution, the integration ratio of each of these peaklets would be 1 to 3 to 3 to 1. 1, 3, 3, 1. Okay, hope that makes sense. If you think about that statistical distribution, it would follow sort of what in math we would call Pascal's triangle. I don't know if you remember drawing these. Like if you do 1 for the outside of the pyramid, and to figure out what the middle of two numbers might be, you just have to add the two, right? Like 1 plus 3 is 4, 1 plus 4 is 5, 5 and 10 makes 15. That would be the ratio you would see for these different multiplicity of split peaks, depending on how many neighboring protons you have. In reality, this is what they look like. Okay, like a quintet is when you have 4 neighbors. The ratio would be 1 to 4 to 6 to 4 to 1, and that's what you see here: 1 to 4 to 6, 4 to 1. Now, if so, what constitutes stuff that protons that actually will split your signal? If the two protons are equivalent, they're not going to split each other, but they could split each other, the two protons on the same carbon, if they're somehow non-equivalent. And maybe you could think of some examples, like remember we talked about the diastereotopic protons. Watch the first video. If the two methylene CH protons are next to a chiral center, those two are not equivalent, so they could split each other. But typical sort of proton distance that you're seeing for the typical splitting is when two protons and the two neighboring carbons are adjacent to each other, right? Like then those are the most typical splitting that you see. If two protons are separated by 4 or more bonds, typically they won't split, unless there's a thing called W coupling. Typically on a benzene ring, what that means is these two protons kind of make a W for Wyoming. Well, actually, not for Wyoming, but like W shape, that they're actually 1, 2, 3, 4 bonds away, but that's kind of an exception when they can actually still have a really tiny splitting, or we call that coupling. When two things are coupled, we say that they split each other by a really tiny bit, but the typical splitting is when two protons are next to each other, like this proton and that proton are adjacent to each other, which by the way, this is an aspirin molecule. And here's a typical proton NMR spectrum. In this case, it's ethylamine. First, I think we've kind of just touched on this a bit, But we also said the same thing about IR spectra. But protons on heteroatoms that are somewhat acidic, that could hop around from one heteroatom to another. They're not really, they're kind of promiscuous in terms of like which exact atom they're bonded to, or which exact molecule they're bonded to, because they're hopping around constantly. That makes that signal very broad. In fact, sometimes it's so broad you can't see it, or sometimes it just kind of almost disappears. So in proton NMR, you don't want to count on figuring much out based on signal that's coming from a proton on a heteroatom. Okay, but sometimes you see a peak like that. Now, protons on carbons, they're always reliable. Okay, so let's break this down. This peak signal corresponding to these three equivalent protons, they would be split into a triplet, because not because there's three hydrogens here, but because there's two neighboring hydrogens that split it into triplet. Now the signal for this CH2 protons, methylene protons, they'll be split into quartet because of the three neighbors. Now I want you to notice that these two NH protons are not participating in the splitting or the coupling, because if they were, this would be like sextet, meaning with 5 neighboring protons, but these don't count in the splitting pattern. Here's another spectrum of this compound. A, B, C, D labeled the different equivalent proton groups. So these two are equivalent because of symmetry, these two are equivalent. These two are equivalent because of single bond rotation, these three are equivalent, again, because of single bond rotation. So we should see 4 signals. D is split into triplet by the neighboring C. C is split into a quartet by the neighboring D. And B here is split into a doublet because it really only has one neighboring proton. Same with A. Okay, so hopefully that makes sense. And another thing that this shows you that I want you to notice is, because it's these two that are coupled or splitting each other, they both have the exact same, what we call coupling constant, often abbreviated with the letter J, and the unit is Hertz. That's the distance between the two peaklets that are split, right? And notice that distance is exactly the same for both of these A and B signals, because they're coupled to each other. Same with C and D, the coupling constants are the same. And so there's 7.6 Hertz distance between these two, between these two, between these two, same with these two and these two. That's the coupling constants, or the split, how far it's split. And coupling constants, those Hertz numbers, they actually tell us a lot about the type of relationships the two coupled protons have. This is the most sort of normal relationship, like especially in an alkane chain. Typically has a coupling constant of around 7, give or take 1 or 2. Like we said, when they're like about 4 bonds away, typically they do not couple or show any coupling constants, unless it's double coupling. So it's around 0 Hertz, meaning it doesn't happen. Now, when you have a double bond situation, it gets kind of interesting. When there's the 2 hydrogens are cis, this table says 7 to 12. It's rarely much more than 7 or 8, usually like around 8 Hertz. But if the 2 protons are trans to each other, typically they have coupling constants of like about 14 to 15. Could be as low or as high as that, but typically 14 to 15 for trans protons. If they're geminal, meaning they're on the same carbon, but because of the double bond, maybe there's something different attached here than here, these two become non-equivalent, because remember the double bond cannot rotate. In that case, the geminal couplings usually are tiny, like 1 to 3 Hertz. Same with when you have an aldehyde, this we would call vicinal coupling, because vicinal means neighboring carbon. Vicinal coupling on benzene is about the same as when it's alkane. There's that exceptional double coupling case, and then if it's on the opposite side, you could basically consider it as not coupling. Now, these tiny coupling constants, like 1 to 3, typically kind of look like this. So here's a doublet that's split into a tiny doublet by some sort of geminal coupling, and this is roughly like 8 Hertz or so. So that's like the normal vicinal coupling, and this is a singlet that's blown up. And with alkenes, often you could see an interesting situation like this, where if you look at the spectrum of this molecule here, this is what it would look like. And because of the stereochemistry around the double bond, the coupling constant is quite different. Like if you look at the A to C coupling, that is trans, right? Remember, that gives you that very characteristic high, big coupling constants like 15. And indeed, in this spectrum, we see that splitting. So here's that big 15 hertz split. So this is, by the way, HA, is split bigly by HC. And then it's split a little bit by the geminal HB. So that's why it's got a big split and a really tiny split, which is geminal. Now, if you look at the signal B, right, this does not have any trans coupling. It just has a regular cis vicinal coupling and a tiny geminal coupling. So it's split by the sort of normal 8 hertz and a tiny 2 hertz for the geminal. Okay. Now, if you look at C, it's got both the trans coupling and a cis coupling. So you see that both. It's split into a doublet bigly, and then that each of those doublet peaklets is split by 8 hertz into doublets. So we would call this a doublet of doublets. Okay. So hopefully you can make sense of that. And that splitting pattern also tells us about the stereochemistry. Like we could assign which one's which, and this diagram kind of tells you about the splitting patterns. It's split in this case, right? Like to explain this peak, it's split into I think that was what was it? The HB is split into the doublet by 7 or 8 hertz, and then split again by about 2 hertz, right? The tiny split. It's a doublet of doublets. You might see something like that with CH2, multiple splitting patterns. It's a triplet of doublets. Why? Because it's got 2 neighbors, vicinal coupling, that splits this into a triplet. Each of those triplet peaklets is split again by the aldehyde neighboring protons, which has a tinier coupling constant. Now, if you wonder, like, how do you calculate the coupling constants from the spectrum, you look at the split distance. Right? This is kind of a small distance in the chemical shift. It's about only 0.01 ppm split. Now, how do you get that back to hertz? You have to remember these hertz chemical shift is converted to ppm by dividing it by the magnetic frequency of the magnet you're using. This spectrum happens to have been taken on a 200 megahertz NMR, so you'd multiply the ppm by the megahertz to get the split distance, which is 2 hertz. So in other words, we're saying this is 2 hertz coupling constant. Now, this coupling constant that split it into a triplet, it's about 0.03 ppm split, which you multiply that by 200 megahertz, which is about 6 hertz, which tells us that this coupling constant is 6 hertz and this coupling constant is 2 hertz. And now we've covered all of these, okay? And so hopefully, now we have to put all these together. Especially, one of the things especially you want to do, remember, is to refer to the chemical shift table. Remember, this will be given to you, but you have to know how to use it well. Let's put it all together in a structure elucidation problem real quick, which we'll do a lot of during class, but I figured it's nice to have an example in the video. Here's a proton spectrum of some unknown compound, but we're given the molecular formula. But remember from Chapter 11, IR and mass spec, you should be able to calculate the molecular formula, and we'll do examples where we'll do all of that from scratch. But for this time sake, we're just gonna start with the given formula. What's one of the first things you should do when you have a formula? If you recall from the discussion about degree of unsaturation, right, you should calculate that. It's very helpful. Now for that, like, you should refer to the, well, mass spec videos, okay, if you forget how to do it. And this comes out to be 0, which tells me, what does that tell me? It tells me there's no ring or there's no pi bond if there's 0 degree of unsaturation. Okay, so that's helpful to know. Now let's take a look at the proton NMR more carefully, maybe starting from the right. There's this big peak, and remember, this is the accumulation of all the integration peak under the area. What you can do in practice, you could measure the distance from here to here, or this height difference by a ruler, and then this height difference by a ruler, this height difference by a ruler, this height difference by a ruler, to figure out the ratio of these peak areas. And I kind of have done that for you, and if you do, this seems to be worth 6 hydrogens, because that's a big height gap. Now, how can it be 6 hydrogens that are equivalent, right? Because a single carbon cannot have 6 hydrogens on it, right? Hope that makes sense. So what are the possibilities? Maybe there could be 2 methyl groups, CH3s, 2 of them, or maybe there's 3 CH2s. Now, you could fairly easily imagine a situation where 2 methyl groups are equivalent because of symmetry, but it's pretty hard and almost basically impossible to think of a weird situation where 3 methylene CH2s are equivalent to each other to make up 6 hydrogens that are equivalent. So this is likely, so my face is hiding at 2 methyl groups, 2 CH3s. This integration here is only worth about 1 hydrogen. That means this height is 1/6 of this height, and it's split into 9 peaklets. It's a nonet, which, by the way, we didn't mention, but this first peak is split into a doublet. That means it's got a 1 neighbor. This has 8 neighbors, so it's a nonet, or 9 peaks. Okay, 8 neighboring CHs, 8 neighboring hydrogens, and this is only worth 1 hydrogen, and it's on a carbon, right? If it's on a heteroatom, we don't see it, or like a singlet or a weird peak. So this is a CH group. This is worth 2 hydrogens, so it's twice the integration of this, and it's a doublet. But more importantly, the chemical shift is around 3.4. If you go back to the chemical shift table, that informs you that it's probably on a carbon with oxygen. And then it's CH2. And here's a singlet. It's kind of in the right ballpark for OH group. It's hard to know that for sure. So often you need the help of IR to identify that you have an OH group. But let's say we have that information from IR, we have an OH group, so this is likely OH. Okay, so how do you do the structural elucidation? Remember we said that this is due to 2 CH3 groups that are equivalent at 0.9 ppm. So these two are somehow equivalent by symmetry, and it's a doublet, which means these guys have a single neighbor, right? So it has a single CH neighbor, single proton neighbor. That's why they're split into a doublet, and there's symmetry here, right in the middle. That's why they give rise to the exact same signal. And there's a CH group here that we assigned, right? This must be due to a 1 CH because the integration is worth 1 hydrogen. That was at 1.8 ppm. Now remember, this guy is supposed to have 8 neighbors. Now there's 6 neighbors, so this must have 2 other neighbors. Let's keep that in the back of our mind, because it's known it. And to put another partial structure on the map, by the way, the key is you start with tiny partial structures like this. This peak tells me that there's an oxygen to CH2. That's worth 2 hydrogens, right? At 3.4 ppm, which was a doublet, which means these guys should have 1 single neighbor. Well, conveniently, we know there's a CH group here that needs another neighbor, so these two must be connected. Then this would have total of 8 neighbors, which would be non-nonet. This has total of 1 neighbor, so it would be a doublet. And there was that OH proton, so that 2.4 must be that, right? So that, sorry, I got out of that. That completes the structural elucidation.